All right, listeners, get ready, because the paper you sent in this time is a wild one. Autoregressive, large language models are computationally universal.
Yeah, it's a bit of a mouthful, but
Yeah.
basically it says that a certain kind of large language model, the kind you've probably even used, can act like a complete computer.
A full-blown computer, not just like a calculator or something.
Right, like a universal computer capable of universal computation, which
Which is
is,
a pretty big deal when you think about it.
yeah. But for those who need a refresher, universal computation means a system can simulate any algorithm or computational process out there.
It's like a master key that can unlock any door in the world of computing.
Exactly. And get this, the authors of this paper, Dale Schuurmans, Hanjun and Francesco Zanini, didn't just talk about it theoretically, they actually demonstrated it.
Yeah, using a real live public LLM called Gemini 1.5 Pro 001.
So this isn't some far-off sci-fi idea, it's happening right now.
It's really happening, and it kind of makes you wonder what else these LLMs are capable of. Right, like how did they even get an LLM to act like a full-fledged computer? That's what I want to know.
Well, there were some pretty big hurdles they had to overcome. One of the biggest was the whole context window issue. You know how LLMs can only see so much text at once?
Right, it's like their attention span is limited.
Exactly. And for universal computation, you often need to process tons of information, way more than can fit in a typical LLM's context window.
So how did they get around that limitation?
They came up with this very clever solution called extended autoregressive decoding. It's like, imagine reading a really long book with a magnifying glass. You can only see a small section at a time.
But you can still understand the whole story by moving the magnifying glass along?
Exactly. And your brain remembers what you've already read to connect the pieces. That's kind of what they did with the LLM. They found a way to make it process information in chunks while still keeping track of the big picture.
Okay, that makes sense, but how does that turn an LLM into a universal computer?
That's where things get really interesting. They use this concept called a lag system, which is kind of like a Turing machine.
A Turing machine, that's a theoretical model of a computer, right?
Exactly. But a lag system has some quirks that make it perfect for this research. Imagine a long string of symbols, like a coded message.
Okay, got it.
A lag system has a bunch of rules for changing that string. Each rule looks for a specific pattern, and if it finds a match, it swaps it out with another set of symbols, then it moves down the string and repeats the process over and over again.
So it's like a really simple set of instructions, find a pattern, swap it out, move on.
Exactly. And the amazing thing is they proved that this simple system can actually simulate any Turing machine.
Whoa, so you're saying a lag system can do everything a Turing machine can do?
Yep, which means it's capable of universal computation.
So by figuring out how to make an LLM act like a lag system, they essentially cracked the code for universal computation.
Exactly. But there was another challenge. Turing machines have this ability to store and retrieve information, like writing notes and flipping back and forth between pages. How do you get a lag system to do that?
Yeah, it seems like a lag system is just moving along a string of symbols. How can it handle complex memory operations?
Well, that's where it gets really clever. They turned the lag system string into a circular queue, like a train going around a circular track.
Okay, I'm visualizing it.
And they developed two mechanisms, one for moving a control token counterclockwise along the track, and another for moving it clockwise, even though the train only travels in one direction.
Wait, how do you make something go backward on a track that only goes forward?
It's like having a conductor walk along the train cars, moving backward relative to the train's motion. To make the control token move clockwise, they came up with this two-timescale message passing scheme. It's a bit technical, but imagine it like having a second conductor who walks much slower, only switching cars after the first conductor has walked the entire length of the train.
So one conductor is like the minute hand on a clock, and the other is like the second hand, both moving counterclockwise, but at different speeds.
Exactly, and by using these two conductors, they could simulate that back-and-forth memory access of a Turing machine. It's pretty amazing how they managed to orchestrate all of this movement within this simple lag system.
It sounds like they choreographed a whole ballet of rules and tokens to make this work, but how did they actually connect all of this to an actual LLM like Gemini?
Ah, that's the real magic. They figured out how to translate this whole intricate dance of the lag system into a language that Gemini could understand.
Hold on, we're talking about an LLM that's trained on text, not these abstract symbols and rules. How did they bridge that gap?
That's where we'll pick up in the next part.
Yeah.
They basically created a special code book to translate the lag system's language into something Gemini could process. And that's when things get even more interesting. So yeah, it's all about teaching Gemini to speak lag system. Remember all the symbols in the lag system, like 262 of them?
Yeah, a lot of symbols.
Well, they had to map each of those symbols to pairs of tokens that Gemini could actually understand.
Like giving Gemini a dictionary or a translation guide.
Exactly. Like creating a secret language where each lag symbol has its own special two-word phrase. But here's the thing. Because they're using these pairs of tokens, Gemini has to output 2 tokens for every lag symbol it processes.
Okay, so it's like typing 2 letters at once.
Kind of.
Yeah.
But then it gets even more complex because remember, some of those lag system rules actually produce 2 output symbols. Which means Gemini sometimes has to output 4 tokens at once.
Hold on. LLMs are usually like those old typewriters. They go clunk after each letter. How do you make one spit out 4 tokens at a time?
That's where the extended autoregressive decoding comes in again. They use this special halt token. It's like a signal telling Gemini, okay, you've generated enough tokens for now, time to move on.
So it's like training Gemini to type in bursts 2 or 4 letters at a time, even though it's technically still going 1 letter at a time.
It's a pretty neat trick. But you bring up a good point. LLMs are usually probabilistic, meaning there's a bit of randomness to their output.
Right. They're not always predictable.
Exactly. But for a universal computer, you need predictability. Every calculation has to produce the same result every time.
So they had to find a way to make Gemini less random.
They did. They basically took away Gemini's creative license by setting its temperature parameter to 0 and controlling all the random seeds. It's like putting Gemini on a strict diet. No more sugary randomness allowed.
So Gemini is on lockdown, following the rules to the letter. But how did they actually get Gemini to run this lag system? Did they have to, reprogram it or something?
Nope. That's the beauty of it. All they needed was the right prompt. Think of it like giving someone step-by-step instructions. They used a really clever prompting strategy with 2 parts, a system prompt and a sliding window prompt.
Good, let's break that down. What's a system prompt?
It's basically like the ground rules, the overarching instructions. In this case, the system prompt contained all 2027 rules of their lag system, all translated into those token pairs we talked about. They basically prepended this prompt to every input they fed Gemini.
So it's like giving Gemini the rulebook before you hand it the puzzle to solve?
Exactly. The system prompt sets the stage for the whole computation. Then comes the sliding window prompt.
This must be how they fed Gemini the input piece by piece, right? Like giving it 1 page of the encyclopedia at a time.
You got it. The sliding window prompt contained chunks of the actual input data. They'd feed Gemini a chunk along with the system prompt, and Gemini would process it according to the rules and generate the output, then slide the window over repeat.
So Gemini gets a bit of the input processes using the rulebook from the system prompt, then gets another piece of the input and so on.
Exactly. Yeah. This way they could feed Gemini arbitrarily long inputs, bypassing that whole context window limitation. It's like giving someone a really long message 1 sentence at a time. They can still understand the overall meaning, even if they're not seeing the whole thing at once.
Okay, so they've got the lag system, they've taught Gemini how to speak its language, they've given it a rule book and a way to process information bit by bit, and boom, Gemini becomes a universal computer. But did they actually test it out to make sure it worked?
Oh, absolutely.
Yeah.
They went through all 2027 rules of their lag system one by one and checked if Gemini, using their prompting method, executed each rule perfectly.
Yeah.
And here's the best part. They published all their code and findings so anyone can try to replicate their results. Talk about transparency.
Wow, that's impressive. So what does this all mean? I mean, we've gone deep into the technical weeds here, but what are the real-world implications of turning an LLM into a universal computer? What can you actually do with it?
Well, that's where things get really exciting. We're talking about potentially changing the world. Imagine having access to the power of supercomputers just by talking to an LLM. You could ask it to design personalized medicine, create super realistic 3D models, or even simulate entire ecosystems to understand climate change better. The possibilities are almost limitless.
It's like having a pocket-sized supercomputer that you can talk to. That's both incredible and a little bit scary, right? What about the downsides? Could this lead to LLMs becoming too powerful or unpredictable?
It's a valid concern. And that's why it's so important to carefully think about the implications and potential consequences as this technology keeps developing. We need to be mindful of the risk while also exploring the incredible opportunities it presents. Things like designing new materials, optimizing energy grids, maybe even cracking the code of consciousness.
Okay, hold on. I need a moment to catch my breath. It sounds like we're entering a whole new world with amazing possibilities and some potential dangers too. So where do we even begin to navigate this new landscape?
Well, the authors of this paper leave us with a very interesting thought. What if all LLMs are inherently universal computers, even before we train them on all that data?
Wait, you're saying that the ability to compute is already built into the very fabric of these LLMs and all the training we do is just a way to teach them how to use it?
Yeah, It's a pretty mind-blowing concept. The idea that we might be tapping into some kind of pre-existing intelligence, it's wild.
It really makes you wonder what else is out there just waiting to be discovered. But let's try to bring this back down to earth for a minute. If we assume, just for the sake of argument, that this conjecture is true, what could it mean for, the future of computing?
Well, for one thing, it could completely change the way we think about AI development. Imagine if we could shift from training LLMs to actually communicating with them.
So instead of force-feeding them massive amounts of data.
Right. Instead of treating them like students who need to be taught everything, we could start treating them more like collaborators, like partners who already have incredible abilities.
And our job is to figure out how to unlock those abilities, to find the right language to communicate with them. It's almost like we've been trying to teach a fish how to climb a tree when it already has the ability to swim across the ocean.
Exactly. We've been so focused on the training part that we may have overlooked the inherent potential that's already there. And if we can tap into that potential, who knows what we might be able to achieve?
It's like we've discovered a new species, and now we need to learn their language, their way of thinking, in order to truly understand them. And not just understand them, but work with them to solve problems that have been impossible for us to solve on our own.
Exactly. We could be on the verge of a whole new era of computing, an era where LLMs help us unlock solutions to some of the biggest challenges facing humanity.
Yeah.
Things like climate change, disease, even the mysteries of consciousness itself.
It's almost too much to comprehend. But with great power comes great responsibility, right?
Yeah.
We need to make sure that this power is used for good, that we don't accidentally create something that could harm us.
Absolutely. Ethical considerations have to be front and center as we explore this new frontier. We need to be very careful about how we design and deploy these systems to ensure that they are aligned with our values, with our goals for a better future.
So it's not just a technical challenge, it's a philosophical challenge. We need to have open and honest conversations about the potential risks as well as the potential benefits, and we need to involve everyone in those conversations, not just the scientists and engineers, but also ethicists, policymakers, the public, everyone who could be impacted by this technology.
Exactly. This is a conversation that needs to happen on a global scale. We need to work together to create a framework for responsible AI development, a framework that ensures that this technology is used for the benefit of all humanity.
It's a powerful reminder that we're not just passive observers in this technological revolution. We are active participants, and the choices we make today will shape the world of tomorrow. But who knows? Maybe this discovery will push us to rethink our own understanding of intelligence. If we find that these computational abilities are inherent in these systems, it might challenge our assumptions about what makes us uniquely human.
It's a humbling thought, isn't it? That maybe intelligence isn't something we solely possess, but rather something we've discovered in an unexpected place. It certainly opens up a whole new world of possibilities, both for our understanding of the universe and for the future of our species.
Well, on that note, I think we've reached the end of our deep dive for today. We've covered a lot of ground, from the technical details of universal computation to the profound philosophical questions it raises. It's been a fascinating journey, and we hope you've enjoyed it as much as we have.
We'd love to hear your thoughts on this groundbreaking research. Do you share our excitement, our apprehension, or maybe a bit of both? Join the conversation online and let us know what this discovery means to you.
And remember, the future of AI is not predetermined. It's something we are actively creating through our choices, our actions, our conversations. Let's work together to ensure that this powerful technology is used wisely, ethically, and for the benefit of all.
Until next time, keep exploring, keep questioning, and keep diving deep.